introduce Monica Quaintance, the head of research and networks at Kadena. Please welcome.
Thanks, Ronan. So thank you for coming downstairs. I know that we had some exciting proof of stake and plasma things going on upstairs. So thanks for taking a detour and coming back to proof of work land. For the next 30 minutes, this is going to be all about proof of work and how you can scale proof of work into a solution that actually does work for a real smart contract platform. So let's get started. So our proof of work system is called Chainweb. And we're going to go into what Chainweb is, how it works, what are its benefits, and then at the end we're going to talk about some work that we've been doing on mining simulations and what mining a network that has the interesting and complicated features of Chainweb really looks like. So what is Kadena? Kadena is, I like to call us the Mac in the land of DIY PCs. So instead of trying to construct a stack full of like, we could build this on writing in Hyperledger on Stellar and use Lightning, like stop thinking about all the components and just use something that's a full stack that works. So we have a smart contract language, we have a public blockchain, and if you're concerned about privacy, you can have a private blockchain with Oracle to public. All of these pieces are connected. We expect to be fully up by 2Q of next year. So what is Chainweb? Our thought behind Chainweb is that if you could do all of the transaction volume that you wanted to do on Bitcoin with smart contracts, then nobody would be bothering with proof of stake. You wouldn't have to be talking about voting and validators and all of these complicated crypto economic schemes that require slashing and other complicated elements if you could just do all of the things that you wanted to do on Bitcoin. And if you could have the kind of transaction volume on Bitcoin, then we wouldn't need to talk about, oh, we're using too much electricity, because it would be so useful. You compare it to how much electricity you use for Swift or ACH or those resources or even the human capital involved in our current capital markets. If we could channel that into only Chainweb, then you could have the kind of network that really is resource efficient. So we say that Chainweb is a solution to Vitalik's protocol trilemma. This is the idea that if you have higher throughput, then you have to sacrifice security. Or if you have higher throughput and higher security, you have to sacrifice decentralization. The benefit of Chainweb is that as it scales, it becomes more secure, and in order to scale, it must become more decentralized. So the way that it works is each chain maintains its own version of state and sandbox. You might call this sharding. I don't use that word because it's been stolen by Ethereum, and now it means something different. But if you mean sharding is having a way to have state in a decentralized manner where state is maintained in multiple places, but then you still have consensus on top, then yes, we are a form of sharding. Miners and participants all use all of the chains, and they mine the whole network. And under the hood, after we have a layer that is going to obfuscate away how the mechanics work, users won't notice that they're switching from chain to chain, but under the hood, that's what they're doing. They're effectively transferring state from one chain to another. So Chainweb is not. Sometimes it's easier for me to compare to other projects and say, this is what Chainweb is, and this is what it's not. We are not side chains, so you don't create a chain and then destroy it. We are not hub and spoke. All the chains in our network are equal, so it's not like Cosmos. We are not an arbitrary DAG. That when people say, oh, you're a DAG, I'm like, yes, all blockchains are in fact DAGs. Bitcoin is a DAG. All things that have to do with directed graphs are DAGs. So we're not an arbitrary DAG. The structure of Chainweb is fixed, and it can be changed by hard forking the network, and we'll talk about that in a minute. But the idea is that because we can choose our graph structure, we can choose the most efficient graph structure, and that's how we get around issues like having eddies in the network, where the network eventually partitions, or having inefficient bottlenecks. We have a fixed graph structure, so we can get around all those issues. And we're not a state maker validator system. So when I use the word node, I mean node in terms of chains. Each node is a chain, not like a node is a participant. So I'm going to show you this picture. It's going to look confusing right now because I haven't explained any of these things, but I'm going to show this to you now so you have an idea in your head, and then we're going to talk through the elements, and then I'll show it to you again. Hopefully then it'll make sense. So this is a sample graph configuration. Remember I said that Chainweb works on any configuration, so we pick the best ones. This is the optimal configuration for 20 chains. And on the right side of that graphic, you have chains that are progressing from left to right, so black to green, and each of these slices is a block height. Just think about that in your head as we keep going. So all of the chains, so all 20 chains in that graph, all add blocks simultaneously. That's how we have throughput in Chainweb. Instead of everybody fighting to make one block, everybody fights to make, in this example, 20 blocks. This allows us to have the throughput features of Chainweb. So the way that the network stays in sync, instead of just being 20 random chains, is they all use the same native token, and at the base layer, peer chains cross-reference each other by passing the proof, the hash, of their previous block to their peers. And we'll get into that with more graphs. So miners mine the entire network. They don't pick just one chain, although you could if you ended up having low hash power. But in general, we assume that miners want to mine the entire network. And users transfer the native token on the network freely from chain to chain, which is how we manage state across multiple chains. If you want to learn more about how we do that, as can be, you should read the paper because we don't have time to talk about this today. I barely have time enough to do this as it is, so read the paper. So, we talked about this a little, but this is important, so it's in red by itself on the slide. The Chainweb protocol is applied to any arbitrary braid. Because we can pick anyone, we can pick the best ones and write those into the structure of the network as the pattern. And as the network has demand, we can hard fork the network to larger patterns, which can give you more throughput without requiring additional energy. So, the base graph is the braid. Remember, we saw the graphic. On the left side, there was a graph. That's the braid pattern. That's how chains communicate with each other. In that graphic, every vertex is itself a chain that will generate a block, and then it will pass the proof of that to its peers, which are the connected edges on that graph. So each edge dictate what peers' previous routes are required to move forward. So you're saying to yourself, wait, you have to wait to get proofs from your neighbors? Yes, you do, which causes a minor bottlenecking issue, except for the fact that we also need to consider balancing the hash power of the network. So having mini bottlenecks actually provides an economic incentive for miners to reallocate their hash power, which we'll talk about at the end of this talk, because that's the research we've been doing recently. Solutions to the degree diameter problem are how we choose the braid, which allows you for maximum propagation to the largest order with the minimum number of messages and the minimum number of hops. So, remember I said Bitcoin is DAG. Welcome to Bitcoin. You have, in this case, we go again from black to green. That's how we generate blocks. So the black block is the genesis block. The red block has a reference to the black one. Blue has reference to the red, which has reference to the black. Imagine that instead of having one chain, you had two chains. In this case, we have the red blocks are both working on both chains simultaneously. They both include references to the black blocks, which is how we share information from each other. If you have two, why not 3? If you can have 3, why not 10? As you get to 10, you start to see the benefits of using these particular graphs as our braid structures, because in 3, you have the same number of messages transferred as nodes, which isn't particularly efficient. In 10, you have 3 messages transferred per node, but you have an order 10 graph. In the 20-chain configuration, remember this picture from the beginning, now we're back and hopefully it makes some more sense. You have 3 messages per node, but you can still get information propagation to your entire network with only 3 block height. So this is how we get confirmation depth in Chainweb. Because if you wanted to reorg the black block, you would have to replace not only that block and its future blocks, you would have to replace all of the other blocks that reference it in the entire network. That's not where I want to go. That's the one I want. So the idea here is that we call this a Merkle cone, which is that the proof from a given block, it's not just a tree anymore. It doesn't just propagate out to a single line. It's multidimensional now. That tree is what gives Chainweb its security property. Remember when I made this like outrageous claim that as we scale, we get more security? You don't lose security with more throughput? That's how it works. Some things here. Here we go. So as the network grows, we can fork out into a larger braid. So this is how we get our claims of transactions per second. If each chain can do 10 transactions per second, and then we have 100 chains, then that's how we have 1,000 transactions per second. If we fork out to larger configurations, you start to see the exponential increases in throughput. So this is the Merkle cone thing. The cone dictates, brings us back to the idea of the mining wanting to be balanced. The Merkle cone is also the shape of the references that you require in order to progress into your next block. So the black block here, if you look to the left of the black block, those are the references that the black block needs in order to be created. So it has to wait for those chains, which means that in the network, you can't get too far ahead. It's like you're doing a really large three-legged race. You've tied them all to each other, which allows for certain of the chains might be more beneficial for people to mine than others, which you would say, oh, you have to wait for this chain, that causes congestion. But actually that chain starts to become very attractive from a mining perspective, because if it's slow, that means that nobody's mining it, which means the likelihood of success for a miner to switch to that chain is increased. I cannot hear you. Can we, I'm gonna try, that's why I'm going fast, try to save 7 minutes for questions at the end, and maybe we'll do that. Where were we? Merkle codes. Right, so this brings us to the question of mining. In mining, the header stream for Chainweb is actually pretty lightweight. All these messages that the nodes are passing to each other, they're just the hash of their own state. And this little tiny hash is what's going over the message queue. So consuming the entire header stream is actually very easy and lightweight. So we assume that, posit this question, large mining pools exist. They do, and we're going to take them into account, and we're going to use them for the benefit of our network. Large mining pools will mine the entire network because it's beneficial for them to minimize the number of collisions on any given block. If a miner finds 2 solutions to the same block at the same time, then they've effectively wasted their hash power. So instead, they're going to distribute their hashing over the entire network. So large mining pools, but we still have a provision for the individual miner with a computer in his closet. The idea is that they would consume the entire network stream and mine a specific subset of the braid. So we have both the provision for large mining pools, and she has a mining rig in her closet. So they allocate their hash power based on the expected payout. We'll talk about this when we talk about our mining simulations. Yeah. So forking in Chainweb. You remember the picture of the graph, the 20-chain graph? Now imagine that starting to fork. It's not just a chain forking anymore. It doesn't create 2 paths. It creates 2 trees. And those trees have different sections of the trees that are compatible with each other. And recombining them has actually been a very interesting problem. We needed a polynomial recombination function of like, oh, these 2 want to combine, but these 2 can't combine. So an example how that might work, we're again moving from left to right, from black to green. The idea is that you have chain 1 and chain 2, and they each make a block. And then moving forward, chain 1 has references to chain 2 and vice versa. So if chain 2 forks, and then they have these 2 references, chain 1 almost immediately, because it's a peer, is going to have to choose between chain 1 and chain 2. So not only is chain 2 choosing who's going to mine it, but chain 1 also has to choose which of chain 2 and chain 2 prime are real. So we do have forks, but they have to be reconciled very quickly. Because of the tight security properties of all these references, forks just don't get very far. Right, so Equilibria mining, we're working with this really great company called Gauntlet. It's a Tarun Chitra's company, and we've been working on simulations of what mining looks like in Chainweb. And so if you have this giant pool of all these blocks that need to be mined, and then a graph of miners and how they communicate with each other, we can simulate different strategies and what they look like from the perspective of miners. So in There are, of course, adversarial strategies like selfish mining. So this is like I only mine the blocks that I make and I only build on top of my own. Or eclipse attacks, like I'm going to keep secret from everybody else the fact that I found a success. And so what we call the beneficial strategy for the network is actually greedy block hopping. This idea that if the event horizon of the chain has a divot because doesn't have enough blocks generated, that hash power will pool to that because it's a greedy strategy for them. So far it's been positive because we actually find that the greedy strategy has been doing very well under the heuristics we've been using, which is the idea that if you wanted to have a return over the risk-free rate, then how would that look like for your potential gains? And so far it looks like actually participating in the way that you're supposed to participate and keep the network balance has such a low volatility compared with any of these other strategies that most people are likely to choose them. You can make a big return if you successfully do an eclipse attack, but the threshold for having a successful one is so high that it's worth it for you to just play along the way you're supposed to, and then you make money. So the opportunistic block hopping is actually what helps balance the hash rate of the network so we don't have bottlenecks. So we're trying to show that the incentives are aligned between keeping the network moving and making money successfully as a miner. So if you are interested in learning more about how we're talking about mining, send me an email. Our papers are on our website. I'm going to move it back to the picture so we can have questions. And I have 10 minutes for questions. Yes. Oh, let me give you this mic and then I can talk.
Hello. All right, so first off, vertical cone's a new term for me, so that's kind of cool. But
we made it up. I'm glad you like it.
so can you just talk about the idea of a miner having to verify all these separate chains and how, for me, it seems like the bottleneck is when you have all these different, separate ledgers and you want to, use the, DAC configuration and get throughput, you're going to have the miners verify all these things before they can use it. Is that true?
There seemed like there were multiple questions in there. I can't move this. That is. So one was verifying transactions.
Sure, because it seemed like they had to verify pretty much a bunch of Merkle roots before bringing them in and being able to build off of them, or
So
have them as valid.
There's going to have to be a validation step in that you have to check to make sure that the root that you got is good, and you're going to do that for the number of peers number of peer chains that are on your network. So in this case, there we go. In the 20 chain configuration, for example, you have to do that for 3 peers. So if somebody sends you a message and says, hey, I found a success on chain 15 and you're chain 1, you're working on chain 1, you're like, cool, let me validate that. You validate that one and only that. You only validate your peers. You don't have to validate the entire network.
So is there an idea of reputation where if this peer is always saying like, hey, this hash is valid, there's a good chance that the next one is also going to be valid from that peer?
Not built into the network protocol because we are not a staking or validator system. But if you wanted to create a mining consortium with your friends, and then if you got a message from your friends who would trust it, like that's your choice as a miner.
Because I'm guessing because I'm thinking from the point of like Bitcoin, where if you run a full node, you're verifying literally every transaction. With this, it seems like
you have to verify every transaction on your own chain.
Yeah.
But you do not verify every transaction on your peer chains. You only have to take the hash of the block and check it against the hash of the block. Right. You don't actually have to unpack all the transactions.
Right. So you're offloading that burden to your peers in this model.
Yes.
Okay, that's like the big trade-off versus a typical, like single chain versus this, right?
But it's proved by math, right? Like you can't fake making a correct block.
Sure, unless you get a block that isn't valid, and then you're just given a hash and you don't know if it's valid or not, right? So I'm not saying that's likely. I'm just saying that's the trade-off. I mean, I'm not saying that's a big deal. I'm just trying to understand.
Yeah.
So, okay.
How do you slice the chains? What is your slicing mechanism? Is it by a functional? Is it by a service? Is it by
Slice
geography?
the chains.
How do you, when you say multiple chains, how does it really work? I mean, theoretically, I understand that this will increase the throughput, but then
Right.
in real world scenario, if there's a miner which is in two different geos, perhaps continent separated, could
Right. So the
still
idea
have
is that
performance
imagine if you spun up 10 copies of Bitcoin, and then you could generate a block on every copy of Bitcoin. It wouldn't matter where in the world you were located. If you were mining all of them, all of the chains are decentralized. They're mined by everybody, and the ledgers are maintained in a decentralized way. They just have a different address and a different hash. So all the chains should be able to talk to each other and be able to mine the whole thing.
Is there a preferred way to slice the chains or not? You don't have a preferred way.
I don't know what slice the chains means.
How do you, when you say multiple chains, how are you designating how is the system designating the chains?
They are created at Genesis. There is one here because then we don't have to move the mic and then we'll move it back.
I have two questions.
Yes.
One is there a set of applications this is particularly good for? And what is it? And the second question is, where is this in development? Do you have a customer yet?
So we started as a private blockchain project, and our eventual goal for this is high throughput transactions that are connected to private blockchain projects. So the idea is like, if you had many people who had smart TVs and you would want to plug them into a wall and be able to share that data, but you wouldn't want it exposed, then you could have that data that's connected to a private blockchain, but then this could handle the throughput of like 1 million people watching Netflix all at the same time. So our eventual goal is to really strategize in the space of high throughput applications that also have a privacy component.
I guess this is maybe the question related to the person in front of me asked, how do you do cross-chain transaction? Or like move coins?
I think I said that if you wanted to know about cross-chain transactions, you should have to read the paper, but I think we have enough. Yeah, we still have 5 minutes, so let's talk about it. So we do it by simple payment verification. We call them actually cross-chain destructive transfers because the way that you move information from chain to chain in this case is, imagine that I had coins on one chain and I wanted to pay you, but you were on a different chain. I would write a smart contract that says I'm paying this guy and I'm paying him 10 coins, and then I would destroy the coins on my own chain. The proof of that smart contract would propagate through the network until it reached your chain, at which point you could redeem your half of the smart contract by verifying it, which would then resurrect the coins on your own chain. That's how we're doing the idea between maintaining state in between different chains. So in this case, I don't have a fixed balance of coins on my chain. You could theoretically have a chain that happens to have no tokens in any of its accounts at any time, and the network still works.
Hello.
Hi.
I'm a little curious. So you said that all these chains are instantiated at Genesis. Is that correct?
So the idea is that we would create multiple chains at Genesis. We haven't decided how big we want to start, but we could start at 100, and then when the network is ready and it's starting to become congested, we could fork out to say 1,000 chain configuration. And we could either generate those chains out of thin air with their own Genesis blocks, or we could fork the existing chains into the new ones, in which case each chain would generate 10 new ones, and then they would just start empty with no accounts.
Can you get a little bit into fault recovery for one of your chains if one of them were to somehow fall offline? I understand that you're saying that you have one of these miners, right? A few of them fall offline, so a few of these vertices are no longer available, or they have less mining power. Can you get into how it is that you deal with that, or how, like, if there was some like terrible catastrophe, like there was a hurricane or something, and all these guys in one location got knocked offline, and this person just completely done. How do you deal with
Yes.
that?
So I'm going back to the Chainweb is not slide, because Chainweb is not side chains, or another way of saying that is each chain is ownerless. If somebody stops mining, what happens when somebody stops mining Bitcoin? They stop mining Bitcoin, and Bitcoin still gets mined by everybody else. This is the idea that everybody who's mining Chainweb is mining the entire braid, so that if somebody drops off the network and stops mining one of the particular chains, like great, free for all for everybody else who now gets to pile on and mine that chain.
Got it. I thought it was something that you said that there were people that were mining specific chains that were adjacent to them, or you were saying they were just doing validation for those chains.
So that's we get some flack from people that are like, oh, this is obviously optimized for large mining pools. You don't care about individuals who like to mine, and that's where true decentralization comes from. So this is the provision that if you wanted to only mine one chain, because that's only the hash power that you had, you could do that. But we don't assume that that's actually how people are going to interact with the network, because it's beneficial for them to mine more than one chain because it minimizes the number of potential collisions.
Got it. So what was the point of having that slide where you had the different vertices that were adjacent to each other, where you were saying they were validating each other, something like that? It wasn't necessary.
So here, and this is the one where chain 1 includes in its header the proof of the previous block from 15, 2, and 6.
Okay, sure.
Yeah.
Got it.
This is how you get like SPVs across and how you keep the network coordinated.
Got it. Thank you.
3 more minutes.
Hi, thanks for that, very interesting. How do block rewards work then? Very simply, I mean, what's the sort of model that you've created for that?
That's a great question. We are still in proof of work Bitcoin land in this room for another 5 minutes. So we do block rewards in that you get paid in the native token of the system when you successfully complete block. Our token has a depreciated schedule over time of how they get mined. So during the beginning years of the network, you get more block rewards, and then as the network becomes more and more mature, the block rewards decrease over time with the expectation that people will have created real applications on here where they pay each other in transaction fees.
So you said that it is possible to increase the number of blockchains by forking all those mechanisms. So how does the genesis block of a new blockchain look like? Does it reference like existing blocks?
So that's a great question, and we're still under development on that one. I'm of the opinion that it should be a branching of an existing chain, which will then reference the account history of what it used to be before the fork. So in this case, out of 20 chains, you might have chain 1 would become chain 1 and chain 2, and then chain 2 would become chain 3 and chain 4, and their account history would then actually bifurcate. But I don't get to make all the calls. I'm just working on research. So eventually our development team will have to pick. But that's a viable path forward.
I was hoping you could talk a little more about how the network resolves forks, in particular how forks don't propagate through the whole chain and bring the whole network down.
Sure. So let's go back to let's look at this one actually. It's interesting. So imagine the idea in which you had, in addition to this structure going on, you had a second copy of this that was branching off. And this idea of chain 1, once you get all the way to the right side of this page, on the very last one, it would have to choose between the blue arrow and the red arrow. You can't have both a reference to chain 2 and to chain 2 prime, because those two are conflicting with each other. And if chain 2 is chains 1 peer, then by the time that chain 2 has sent these blocks out, chain 1 has to immediately generate its next block, which means it has to pick one or the other almost instantly. It's not like, oh, the network can go move some sort of distance and having this problem of resolution between the two of them. In a way, we're sacrificing a form of liveness for safety, because almost immediately chain 1 is going to have to pick one or the other. And because these resolutions happen so quickly, that they can't, like chain 2 prime is just not going to survive if chain 2 is the one that's picked by chain 1. And because of the references, these reconciliations have to happen very quickly after they originally occur.
My question is kind of like what happens when there's chain 3 and then chain 1 picks chain 2 and chain 3 picks chain 2 and 5, and you have all these
drawing this graph out to the side, and like if you added chain 3 and chain 3 prime and then there was a collision in there, they would have, the next one would then have to pick one or the other, because you can't survive having these trees very long before they recombine into a place where you have to reconcile the fruits. We could like draw out the tree there. It's a good one.
Time check. For what last question?
Okay, one more question. Last one.
Over there. Going back to the block reward real quick. So say the network is like initialized at 100 chains, and then you fork to say like 1,000 chains. How does that affect the block reward?
So the amount of coins that will be mined over time it's a fixed function. So that would decrease the reward that you get per block at that time, but it also vastly increases the number of potential successes at any time. So you as a miner, instead of working really hard with competition to make 1 out of 100, can have significantly less competition to have 1 out of 1,000. So it